Thanks everyone for coming out. As you can probably tell, Quilt Day is still somewhat an informal event, which I think is a good thing. But it's getting bigger. And for example, we have Travis Taylor coming from Alabama to visit us, and there'll be other out-of-town guests tomorrow as well. So this is also meant to be an informal tutorial, even though it's being Facebook Live, which somehow makes it more formal.
It's not live, it's just...
It's not live, but it's recorded. So with that in mind, just stop me and ask questions, and I will just stand here for as long as you can tolerate me, you know, maybe past 8:30 if you want. At some point, the talkers are supposed to come. So this is a tutorial that I delivered this at a conference in Barcelona, and for that event, each person attending paid $100. But I think if we would have done that here, no one would have attended, and instead we bribed you with tacos. So I'm glad that we had a good turnout. Okay, so without further ado, this talk is meant to cover the basics of quantum information, thinking of qubits in an abstract way. Okay, sort of these basic units of quantum information that we can process. And the goal is to get to quantum communication theory. That's what I'll talk about towards the end. But for the beginning, we'll just talk about some basic concepts. Okay, some of which you might have already seen, and maybe that's a good thing, and some of which maybe you have not. So the main questions motivating this work, and at least my research in the field of quantum communication in general, are to determine what are the limits of communication that are imposed by physical laws, and in this case, quantum mechanics, okay? And then also, along with that, in addition to trying to figure out the limits, you're interested in figuring out ways to achieve those limits. Okay, so what are the ultimate limits in principle for communication? Major applications are quantum key distribution. So this is something that was discovered in 1984 by Charles Bennett and Gilles Broussard. It's a method for secure communication using the laws of quantum mechanics. Also, you might be interested in this if you're trying to shuffle qubits around in a quantum computer. Knowing the limits of communication are important to figure out how you're going to efficiently shuffle these qubits around in a local quantum device or for a distributed quantum computational task. Okay, so to address these questions, we have to consider quantum mechanics, and then we're naturally led to this really beautiful intersection of information theory and quantum mechanics that's now known as quantum information theory. Okay? And one of the goals in this program is to distinguish what is different between quantum information and classical information. Okay, what is it that you can do quantum mechanically that you can't do classically? That's kind of the most interesting question. And generally that's the question that quantum information science tries to address. Okay, so what are the tasks we can do with quantum mechanics that we cannot do without it? So there are a long list of examples. There's the famous Bell inequality, the Bell theorem. I'll talk about that. That can be reformulated as a game that we'll play. There's also these basic communication protocols like superdense coding, teleportation, more advanced things related to cryptography, data locking, data hiding, and of course quantum cryptography. Okay, so some sort of historical aspect, if you haven't seen that before. I want to trace some of the history of how quantum information came about. It's kind of curious that the founders of quantum mechanics, this notion of quantum information hadn't really surfaced to become a concrete concept. There were ideas definitely there. Schrodinger dealing with notions of entanglement and steering, and Einstein as well. So I would say one of the principal starting points was the Heisenberg uncertainty principle. That's kind of one of the things underpinning the security of quantum key distribution. Okay, the fact that you can have this fundamental uncertainty. Okay, Then quite a bit later came this famous EPR paper, and they were questioning whether quantum mechanics is complete, in the sense that they thought that they came out with a sort of counterexample to the uncertainty principle. So they thought they came up with a scenario where you could measure position and momentum simultaneously without any uncertainty. Okay, and it turned out that at the time they didn't really fully understand this phenomenon of quantum entanglement. Okay, the original Heisenberg uncertainty principle applies to a single particle. Okay, but they were trying to apply this single particle uncertainty relation to a two-particle scenario where you have entanglement. Okay, and then that's where it led to some confusion. Okay, so they put out this paper in 1935, and then people thinking about the foundations of quantum mechanics were concerned about it, but I think for the most part, everyone else doing physics, maybe they just thought it was some funny thing and didn't really understand it. Then quite a bit later, Bell came out with his famous theorem as an answer to this paper of EPR. Okay, it showed that if you it showed essentially that EPR was wrong. Okay, that they thought of the world as you could describe the world with what's called local realistic theory. Okay, and then Bell said, okay, let's suppose that you make those assumptions for the theory. Then he came up with an experiment that could be conducted to prove that the world doesn't behave according to the EPR theory of local realism. Okay, and so this Bell theorem is not, now we understand that it's not just a foundational thing, but it applies to, it has applications to secure quantum key distribution, for example.
So, I was wondering when I looked through your slides, why didn't you skip from 35 to 64 here when in 47, both Dirac and then Price Ward actually did the experiment with gamma rays into a calcium target and created an electron-positron pair and demonstrated the entanglement source?
Well, at that point, I don't know if the entanglement was fully understood. And with Bell's theorem, we can really say that he was sort of the first quantum information theorist, in the sense that he was trying to give a task for which classical mechanics could not achieve that task, but quantum mechanics could. So quantum mechanics, we can rephrase it as a game, where in quantum mechanics you have a greater chance of winning the game. And so in that earlier experiment, I don't know if that concept had come into play yet.
Well, certainly not Bell's inequality, but in 47, the Price Ward paper did demonstrate, and it was the first time the word entanglement was used also.
I see.
No, entanglement had been used by Schrödinger much earlier.
It was, yeah, so Schrödinger it used a German word for it, and then it was sort of, I guess, transcribed to English. Yeah, certainly. I mean, entanglement was there, and it's a phenomenon. It's a physical phenomenon. It existed before Bell, right? And so it was just this understanding. I would say it didn't come along until Bell. Okay, and then if you start thinking in an information theoretic way, which is what we'll do later, and quantify things in terms of entropies. People at ETH Zurich, they came up with a revision of the uncertainty principle that applies to two-particle systems, and it incorporates the phenomenon of entanglement. Okay, so this phrasing in terms of entropies, that's only a decade ago that this came along. Okay, so there's still many things at a foundational level that are being understood in current times. Okay? And then there's this history of the von Neumann entropy as some way to quantify uncertainty that had motivations in statistical mechanics. Later, Claude Shannon kind of rediscovered this formula in a completely different context. He was an engineer, a communication engineer working at Bell Labs, and he was trying to figure out the ultimate limits of communication lines, right? So at this company, they're trying to figure out how do you send data over communication channels. And Shannon rediscovered this formula, and then there's this famous story, I've read it many times, where Shannon actually went to von Neumann and he said, hey, I have this quantity that I found, what should I call it? And then von Neumann said, well, you should call it the entropy for two reasons. First, I found this years ago. You know, Shannon's work was in 1948. So von Neumann said, first, I found this years ago in the context of statistical mechanics. And second, you should call it entropy. No one understands what that means, so if ever there's a debate, you'll have the advantage. So that's how the story goes. So that's the, you know, of course this quantum entropy is this ubiquitous formula that appears in many different contexts, including quantum information theory, and we'll get to its use and meaning later. Then came along a notion called quantum relative entropy. This extends the entropy. It's an entropy that's relative between two quantum states. Okay, and so this was formulated in a mathematical physics paper in 1962. And then came along these fundamental information inequalities. So these are these fundamental quantum information inequalities proved. There's this thing called Strong's additivity, which underpins most of our understanding of information processing, the limits of information processing using quantum systems. Okay, so I'll discuss what this Strong's additivity is and means later. And then related to it, very intricately related to it, is what's called data processing for quantum relative entropy. Okay, and so these can be thought of as akin to second laws of thermodynamics. They place limitations on information processing. Okay, and then in the 1970s, these a more refined understanding of quantum measurements came along. The formalism of quantum measurements and similarity measures for quantum states. This was the work of people like Hellstrom, Halevo. I put this there because when I gave the tutorial in Barcelona, it was in 2016, and that was the year that Halevo won the Shannon Award, and he was the first quantum information theorist to win the Shannon Award, so it was a nice celebratory time. Okay. And then information theory, this is sort of going on somewhat in parallel to these developments, but a little bit later, right? So we talked about Shannon. What did Shannon do in a breakthrough paper in 1948? He set the foundations for information theory. There are tasks like data compression, you know, classical data compression. Where do you see that now? You know, if you send JPEG files, if you send zip files, those ideas are there. Okay. And then he also determined the limit for communication over a noisy channel. And that's called the communication capacity of a channel. Okay? And so he solved these tasks, these information processing tasks. And then what he did is he showed that the answer to data compression is the entropy of a probability distribution. Okay? So this sort of complicated task is a very beautiful answer in terms of this entropy formula. Okay? And then the channel capacity communication task is a very nice answer in terms of a correlation measure called mutual information. Okay? And we'll talk about those things later. In Shannon's work, he only considered classical physics without quantum effects. So that was how he modeled things, and then he arrived at his formulas. And so his work and that of others that came later we got to questions like these. How do quantum effects enhance communication rates, right? So this is a sort of fundamental quantum information theory question, right? How can you use quantum effects to enhance security, right? So that's related to quantum key distribution. Maybe you're trying to figure out what are the limits of quantum key distribution. Okay. And then what are some tasks that simply don't have a counterpart in the classical world? Right? So we already talked about the Bell's theorem and the game that's associated with Bell's theorem. So that shows a very distinct separation between classical and quantum. Okay. So the overview of this tutorial, and I've already used a fair amount of time. This is what we're going to try to get through, and we'll just see how we go. So we'll start with an overview of the basics, quantum states and quantum channels, sort of these abstract notions of quantum information processing. Then we'll get to these protocols. So the Bell game associated with the Bell theorem, and it can be reformulated as this CHSH game, which is something you can actually play, right? So we'll play that. And then we'll talk about some basic communication protocols. Then we'll talk about things like distance measures for quantum states. So why is this important? If you're trying to simulate some quantum algorithm on an actual quantum computer, what you're going to end up doing is some kind of approximation of that. And so you want some way to judge the quality of the approximation, and these distance measures can be helpful for that, right? So there's like an ideal state that you're trying to make, and then there's the actual thing that's realized by the experiment. And you can use these distance measures, like fidelity is a very famous and popular one, as well as something called trace distance. Okay, then we'll talk about information measures. We already discussed entropy, mutual information, that will fall into this discussion of information measures. Then we'll talk about this fundamental task, quantum data compression. Okay, so this is something that was formulated in 1995 by someone named Ben Schumacher. And Schumacher is the person who invented the term qubit. Okay, it started out as a joke, and then it caught on. He was joking with his friend. It was some car trip after a research visit. He was joking with Bill Wooters. He said, "Wouldn't it be very funny if we could call this qubit, like in the Bible? You know, qubit was a measure of distance, but with a C." And then he thought about it, and he thought to himself, "That's actually a really good idea." And so then he called it qubit. We measure quantum information in units of qubits. Okay, and so the name stuck, and that's what we use now. Okay, then if there's time, we'll talk about these different communication tasks, communication over quantum channels, and that'll be it. Okay, so let's go right away to this review of the quantum formalism. So what do we need to do? We need to understand the basic objects formulated in abstract language. So we'll understand quantum states and then evolutions of quantum systems prepared in certain quantum states. Okay? So the states are represented mathematically by density matrices. Okay, so a density matrix in some sense generalizes a probability distribution. And then the evolutions will be characterized by quantum channels. So this incorporates the standard unitary evolution that arises from the Schrodinger equation, but also more. It incorporates evolution of open quantum systems that are interacting with their environment. Okay, so these ideas extend, we're saying that density matrices generalize probability distributions. They have a richer structure. Kind of the reason you can do more with them, because there's more room in Hilbert space to play with. And these quantum channels generalize evolutions of classical systems according to classical channels. Okay. By a classical channel, I just mean a conditional probability distribution, right? So if you input like 0 to the channel, it'll have some stochastic behavior, right? There'll be some probability that outputs 1, probability that outputs 0. If you input 1, there could be a different behavior. So that's a conditional probability distribution. So quantum channel generalizes that. Okay, and then here's the thing. Everything that classical can do, quantum can do, right, in principle. So, and it can do better, right? There's this famous song, anything you can do, I can do better. So anything classical can do, quantum can do better. Okay, because there's more room in space in the Hilbert space to play with.
Although that's a little stretch, because classical physics has inherent nonlinearity, which quantum physics doesn't.
Well, these nonlinear evolutions can be incorporated. So any nonlinear function can be embedded into a reversible function, which can then be embedded into a unitary evolution. But this is a separate, maybe this is something we should discuss offline. But any stochastic evolution can be understood as a quantum channel. So any kind of probabilistic evolution can be modeled as a quantum channel. Okay, let's start with quantum states. So basic object density matrix, usually we use the Greek letters, rho, sigma, tau, omega. Rho is usually used for density, so that's why we associate it with density matrix. It's a square matrix. What are its properties mathematically? It has to be a positive semi-definite matrix. What does that mean from linear algebra? The eigenvalues of that density matrix have to be non-negative, right? So this is what we write. If all the eigenvalues are non-negative, we use this symbolic notation to say that means positive semi-definite operator, okay? And when you take the trace, the sum of the diagonal elements, the trace has to be 1. Okay, so why don't we write this down? So it has to be positive semi-definite. So in particular, it's Hermitian. What do we know about Hermitian matrices? They can be diagonalized, right? They can be diagonalized. So rho, you can write like this: U, and then some list of numbers. If it's a D by D matrix, and some unitary matrix. Okay? So these P1 through PDs are the eigenvalues, and we demand that they're non-negative, okay? Just like a probability distribution, right? And then the trace, if you take the trace of this matrix, there's something called cyclicity of trace. The U dagger will wrap around with the U, they'll cancel, make the identity, and then the trace is just the sum of the diagonal elements. Just like with a probability distribution, when you sum the elements of a probability distribution, they sum to 1. Okay? The dimension of the matrix, in this example, we took the dimension to be D. What does that correspond to in an information theoretic sense? It's the number of distinguishable states of the system. Okay? So, for example, with a qubit, D would be 2. You would just have this, a 2 by 2 matrix, right? And then there are 2 distinguishable states of the system. So you can embed a classical bit, 0 and 1, 2 distinguishable states, into a qubit. Turns out that's the most you can do. There's something called the Halevo bound, which Halevo proved in 1973, that connects with this notion of distinguishability of quantum systems, of states of quantum systems, and how much classical information you can encode into a quantum system. Okay, so if it's a D-dimensional matrix, you can encode D distinguishable states. In terms of bits, that would be the binary logarithm of D, that number of bits. So if there were 8 distinguishable states, you could have 3 bits. Okay, and we talked about qubits. So in the information theoretic sense, we want to distinguish between sort of the physical qubit and the notion of information qubit. So the physical qubit is what gets encoded into a quantum system. For example, the polarization of a photon, the spin of an electron, that would be the physical embodiment of the qubits, right? It has to be realized somehow in the physical world. And then this density matrix characterizes the information stored in the qubit. Okay? And we'll talk about that a bit more. And then we already said this. A classical bit has 2 distinguishable states, 0 and 1. They can be embedded into a qubit. So anything we can do with classical, we can do with quantum. What is the interpretation of the density matrix? So everything, the numbers that are encoded in this density matrix, you can use those numbers to predict the outcomes of experiments that you conduct on a system encoded in that density matrix. Okay, so the results of the experiment will not be deterministic, right? That's one of the fundamental things with quantum mechanics. They'll be probabilistic, and so what we predict are the probabilities that you'll observe over many repetitions of an experiment, right? So you do many repetitions with the quantum system prepared in the same way every time, and then you start collecting statistics over a large number of runs. The probabilities that you observe will agree with the probability, the frequencies that you observe, the empirical frequencies that you observe will start converging to the probabilities that are encoded in this density matrix. Okay? And we already said this, it generalizes a probability distribution. And then how do we embed a classical probability distribution into a quantum system? We could say there's some standard basis that we encode information to. So if we say that the U is the identity, and then we say that there's some standard basis or some standard frame of reference, that's how we can encode classical information into a quantum system. And then when we incorporate these unitary rotations, that's how we can go away from that classical fixed basis. Okay? Okay, this is just meant to be a break. This is a picture of, it's no later than 2016 because I did not update the tutorial, I'm sorry. And I actually forget where this, oh, it's UC Santa Barbara. Okay, so they're making good progress on building superconducting qubits. Maybe one thing, I think a lot of you are familiar with this, but there are companies, major companies building quantum computers, Microsoft, IBM, Google. At least with IBM, you can create an account with what they call the quantum experience, and you can play with their superconducting qubit quantum computer. I believe they have 50 qubits. Yeah, 50 qubits. And so I played with it in 2015 when they had 5 qubits. So that's quite a bit of difference. Okay. Good. So what are some examples of quantum states? We can embed classical into quantum, so that's what we'll do first. So we're obliged to introduce this funny Dirac notation, which I think many in the room are familiar with. If you're not, then you just sort of get used to it. It has its value. Once you get used to it, you really get hooked, and then you can't think in any other way. So that's just how it is. So what you do is you say, let's call this Dirac ket 0, assign it to this unit vector, and then the bra will be the dual of this unit vector, what you get when you take the conjugate transpose. Okay? And then to make a density matrix, you glue the bra with the ket, so that means the outer product of this vector with this one, you just multiply the vectors in the linear algebra way, and then you get this density matrix. So that is the density matrix for a deterministic classical bit in the state 0. Okay? So that's how we embed classical into quantum. And then you can do a similar thing. We'll use the 1 in the ket to denote this vector which is orthogonal to this one, and that corresponds to distinguishability of the classical states. Okay, so that's 1. And then you take the conjugate transpose, you call that the bra, you glue them together by the usual linear algebra multiplication, and you get this density matrix. Okay? So when you multiply the density matrices, the answer is 0. So it means that those states are orthogonal. Okay? And if they're orthogonal, they're distinguishable by an experimental procedure in principle. Okay. So we embedded classical into quantum. We can think of the state rho 0 as 0, rho 1 as 1. If that's all we could do, that wouldn't be very interesting. So another thing you can do is take probabilistic mixtures of quantum states. Okay? So what do I mean by that? Somehow you have some uncertainty, right? Like if I flip this coin, and then you don't know what it is, how would you describe the state of this classical system? You would describe it as well, you could describe it as a density matrix with 1/2 along the diagonal, right, along each component. So that would be a random mixture, that would be a random bit embedded into a quantum state, okay? And then mathematically, that means that the state space of quantum states is convex. So it's a very nice mathematical property to deal with. Often we're tasked with optimizing certain functions. How much, what's the maximum rate of information you can send? Optimize overall density operators, right? It's a convex space, and so those are nicer to optimize over.
I'm not familiar with the term convex.
Convex, it means if you have two things, if you have 2 points, you can connect them with a line, and then any point on this line is the convex mixture of those 2 lines. Okay, so convexity just means probabilistic mixture. And then mathematically, it just means if I have one density operator and another, then I can take this linear combination of them, which is called convex combination, and then that's a legitimate density operator. So it's like, the experiment was prepared in sigma 0 with probability p, and sigma 1 with probability 1 minus p, and you don't know which one, so you say it's described by the convex mixture of them. All right, so that's what we do with the coin flip. Good. So then for our classical example, if we take the convex mixture of 2 classical states, it corresponds, we would write it like this in the Dirac notation. In the matrix notation, it just means p is along, there's probability p for it to be in the state 0, right? And probability 1 minus p for it to be in the state 1. So with the coin flip, we set p to 1/2 if we really don't know anything at all. Okay, so what we've done is we've said, okay, not only can you embed the state of deterministic classical bits into quantum states, you can embed also the state of probabilistic bits into quantum states, right? This is a probabilistic bit. It's a legitimate density operator, so it's all good. Are there other kinds of quantum states possible? If this were it, then we would be restricted to a probabilistic classical theory, okay? And so we would be limited. So there are other kinds of quantum states, and you can do things like this. So I'm sticking to this rule throughout the tutorial as referring to density matrices as the state. Okay. When you take quantum mechanics, you can also say the state is described by a wave function. Those 2 pictures are in correspondence, but for the purpose of this tutorial, we're saying that the states are described by density operators. So how do you construct more interesting quantum states? What you can do is you can take a unit vector and take a superposition of those classical bits, okay? This is distinct from, what we'll call mixture of 2 classical states. This is what I'll call probabilistic mixture of 2 classical states, and this is what we'll call a superposition of 2 classical states, and we'll see the difference, okay? So what are the requirements? Alpha and beta have to be complex, and the sum of their squares should be 1. There's a very interesting story about how this rule came about. It's called the Born rule. And some of you might have heard it, but if you haven't, I find it nice. So Born, in his paper where he came up with the Born rule, where he proposed the Born rule, the original version, he didn't have the squares. He just had the absolute values. And then the paper went out review. I don't know what the referee reports were like. Actually, I don't even know if they had referee reports in those days. No. So, some time went by, right? And I guess nobody said anything. I don't know the full story, so I have to embellish a bit. And anyway, some time went by, the final proof of the paper came in, and then he sort of realized, oh, that's not right, it's just wrong. So he put in the squares in a footnote, and then that became known as the Born rule, and then that's what he won the Nobel Prize for. Right? So check your papers carefully in every stage of the publication process. You know, you send it out to review, you send it to your co-authors, the proofs come back, check every detail, right? You never know what you might find. Okay, so then you take the you take this unit vector and you glue it with itself, right? That's what we did in the previous slide. We took the classical bit and we took the linear algebraic product, the outer product. We do that with psi. What do we find? We find the off-diagonal elements, right? So that's a way to distinguish classical from quantum, right? Any classical bit we would embed with respect to some basis, in our case the standard basis, and the only possibilities were the terms along the diagonal, which were just the probabilities. With superposed states, you can have the off-diagonal terms, and those are called coherences, okay? Because you realize what's called this coherent superposition state. Okay. And a very important point to make is that this superposed state, this density matrix resulting from this linear superposition of these two kets, is physically distinct from this state if the coherences weren't there. So if you were to do experiments to try to figure out, okay, do I have this state, do I have this state, there's experiments you could do to distinguish this one from this one. And you would observe physically distinct outcomes. Okay? All right, and then there's a very useful notion called the Bloch sphere. And what you do is you form these Pauli matrices. Okay, so one Pauli matrix is simple; it's the identity matrix, and then you have x, y, z. This is the same as sigma x, sigma y, sigma z if you've taken quantum mechanics course. And these are very important to study and understand their properties. Okay, so they have eigenvalues plus and minus 1, and their eigenvectors, we abbreviate them in this way. So there's a state called the plus state, and that's a uniform superposition of 0 and 1. Okay, and then if there's a minus state, which is different, so that's 0 minus 1. So if you were to do the, if you were to write things out with the linear algebra, the minus state would be like this. Right. And then you would do this. So that's what I mean by minus. And then those are the eigenvectors of the Pauli X matrix, and the eigenvectors of the Pauli Y matrix are these right here. Not only do you have plus and minus, but the complex I. And then 0 and 1 are the eigenvectors of Z. Okay? And so what we see is that there's a correspondence between the eigenvectors of Z and the classical bits that we were talking about, right? This is how we represented classical bits. Okay, so there's a very interesting construction called the Bloch representation of a qubit. And Professor Rao will talk about this more tomorrow during his overview of his research and interesting ways to extend it. So the state of a qubit, remember that's a 2 by 2 matrix. There are constraints on it, that it's positive semi-definite, there's trace 1. And what you can do is translate those constraints on the entries of rho to constraints on these real numbers r, y, and z, rx, ry, rz. Okay, and so the constraints on the constraints of positive semi-definite and trace 1 translate to this rx, ry, rz has to be some vector in the unit sphere in 3-dimensional space. Okay, so that's a very nice representation. and it allows you to visualize the evolution of a qubit. If there's a unitary evolution and the state is a pure state, the state will be going around the sphere, the surface of the Bloch sphere. If it's a noisy process, maybe the state of the qubit can be visualized as starting off on the surface of the sphere and sort of degrading to the middle of the sphere. Okay. So this is how we can write it. Here's the x-axis. On the x-axis are the eigenvectors of Pauli x and Pauli z. Sorry, the plus 1 eigenvector of Pauli x and minus 1 eigenvector of Pauli z. And then the y-axis, you have the eigenvectors of Pauli y, and similar for the z-axis. Okay, and so you can you can parameterize the state of a pure state qubit. We haven't talked about that yet, but it's the state of a qubit that's on the surface of the sphere. Okay, you can parameterize that by 2 angles. Okay, and then there's the state that we talked about previously, right? I flipped the coin, and then that was the random bit, right? So the random bit is the uniform mixture of classical 0 and classical 1. That's an identity matrix. That identity matrix, when you translate to this picture, if the state is the identity matrix, that means there can be nothing here, nothing here, nothing here. So the all 0 vector. That's the middle of the sphere. Okay? So what that's called maximally mixed state. It's the random bit state, random qubit state, call it chaotic state. That's at the middle. And so that's, the state is sort of completely unpredictable. Classical states, the probabilistic states, the probabilistic classical states that we talked previously, we said, you have convex mixtures of 0 and 1. That's the line connecting 0 and 1, right? So if you're just classical, you see how restricted you are, right? You're in this 0 measure, there's so much more that you could explore, right? Like there's the whole volume of the sphere that you could explore in quantum mechanics. So if you're just classically listening. Okay, and then this is a term I used previously. We say that a quantum state is pure if it's on the surface of the sphere, and otherwise it's mixed. Okay.
But aren't 0 and 1 on the surface?
They are, yeah. They're pure, deterministic classical states. Yeah. So those are the only pure states in a classical theory, right? Where you just have a bit.
But in the quantum world, the infinite points on this.
Yeah, the whole sphere, you have many, many more, so it's much richer. Okay, and then I guess previously, I don't know if I said it, but this is a pure state. If it's just this side taken with itself, that's a pure state. If you're going beyond qubits. Okay, let's talk about higher dimensional quantum systems. In some sense, we already did that. We were talking about these d-dimensional states over here. So we could write a state of d dimensions in this way, where what we've done is we're using this Dirac notation, right? So you have I, that corresponds to the standard basis vector, where you have a 1 in the ith. Sorry, if we start counting from 0, it would be the I plus 1 slot, and you have zeros elsewhere, right? So that's this basis, and that's an orthonormal basis, and that's how you can have classical bits encoded into using these vectors, right? But a general quantum state we can write like this, and these rho ij's are the matrix elements. So if I were to just write out the matrix, we would have rho 0, 0. I guess I'm using the superscript. And this is also something we talked about previously. Since every density matrix is required by definition to be positive and semi-definite, and with trace 1, there's this powerful theorem from linear algebra that applies called the spectral theorem. The density matrix has a spectral decomposition in this way. So this right here is a different way of writing what we wrote previously. Right, so what we wrote previously, if we want to translate it to this language, we could say the part in the middle is this. X and X. Where these are the vectors with respect to the standard basis, right? And then the phi x's are what result from the unitary acting on X. Okay, the unitary that you get from the spectral decomposition. Okay, so that's how we, bridge with notation.
Sorry, question about notation. So what is this? There is a P big X, little x. So what does?
Oh, I'm sorry. Yeah, so I adopted this notation. This was sort of ingrained in me during my PhD work. X is a random variable. Big X is a random variable. Little x is the realization. And so you write the probability distribution as, the probability for getting, observing outcome realization X from the random variable big X.
Okay.
And so this big X is somehow associated with the probability. Okay, so some notation. Yeah, please stop me for any notational things. Because there's obviously a lot. Good. And then we said this previously. Density matrix is pure if there's a unit vector such that you can write the density matrix in this way. Otherwise, it's mixed. So with respect to the spectral decomposition, it means that this probability distribution is degenerate. It's equal to 1 for one of the probabilities and 0 for the others. So if you were to write out the sum, there would be only one pure state in the decomposition. Okay, slight little break. This is a picture of the IBM 5-qubit quantum computer maybe I used it in 2016. See, I'm losing track of time. It would have been impossible unless I was a time traveler. So anyway, this is a picture of their 5-qubit quantum computer. And why am I showing this? Well, we've only talked about single quantum systems so far, right? So that's kind of perhaps boring. You can't really do much with a single qubit. You need to put them together and compute on them to do more interesting things. So we need to figure out how do we describe the state of a multi-qubit quantum system.
So where are the 5? Can you point to? I see.
That's what I think it's
I see
1,
instructions.
2.
Yeah, I see. Either way I look at it, I see 4s or 6s.
Right.
Maybe one is an extra in case or something.
You do need a lot of error correction. It could be that these are some ways of like some of these boxes are ways of connecting the qubits. I don't know the answer, I'm sorry. We'll leave that as a homework exercise. Okay. So how do we describe the state of multiple quantum systems? Classically, what would you do to describe a classical bit? Multiple classical bits, you would take the Cartesian product, right? So you would take the Cartesian product of 0 with 0, 0 with 1, etc. And then the state of the state of 2 bits would be 0, 0, 0, 1, 1, 0, etc. But this Cartesian product is not rich enough to capture what can happen with quantum states. In particular, we talked about you can have superpositions of quantum states, right? And so the Cartesian product is not rich enough to capture this. So what can we do? So let's think of this is somewhat abstract right now. if we have two classical bits, they can be one of these four possibilities, right? And the thing that we saw previously is that we could make superpositions of these possibilities as long as we obeyed the Born rule, right? So you can put any complex numbers here, alpha, beta, gamma, delta, as long as the sum of their squares is 1. But when we write this, what does this mean? You know, what does this mean mathematically, right? So the point is that you can't just use the Cartesian product. You need a generalization of that called tensor product. Okay. So the tensor product is defined in this way, and we're defining it with respect to the vector picture. You know, not the Dirac notation. Okay. So, but what does it mean if I have a two-dimensional vector here and two-dimensional vector here? How do I do the tensor product? I take everything over here and just place it on top of what's on the left. So the right goes on the left. Okay. Everything on the right goes on top of the scalar. So that's what I'm doing right here. I put the right, put it on top of the left, put the right on top of the left, and then you multiply it out. And then that's how you can define the tensor product mathematically. Okay. So if we use this definition, which is what we should do, then the state that we wrote previously can be described like this. Why is that? Let's show an example. If we take 0 tensor with 0, we get, you know, we said 0 was defined like this. Then we tensor them together, take the right, place it on top of the left, and I'll get 1, 1, 0. And it just works out to that. Okay. This is the kind of thing you do when you're starting out, but eventually you really want to abandon this because it becomes very cumbersome, and you sort of work directly with properties of the tensor product and the Dirac notation. This is where I think the Dirac notation is helpful. Okay, so if we do that exercise for each of these terms, we would end up with this on the right, right? So alpha, beta, gamma, delta. Okay? That would be the vector, the unit vector corresponding to a 2-qubit density operator, right? To get the density operator, we take the unit vector, its outer product, this thing right here, and then that's a density operator corresponding to that vector. This is a pure state, okay? It's very helpful in quantum information to put system labels. One of the important questions is always when you're trying to solve some problem in quantum information, who has what, right? Who has what? So it's a 2-qubit system. That means, you know, one person could have 1 qubit, another person could have the other qubit, right? So with this notation, we're saying, oh, Alice has the first qubit, Bob has the second qubit. Okay. But what we see is that in the definition, they're somehow intertwined, right? Like we can't say if there's an arbitrary alpha, beta, gamma, delta, then Alice has 0, Bob has 0, right? If it were the case that beta, gamma, delta were 0, and alpha was 1, then we could say, oh yes, for sure, Alice has 0, Bob has 0. But if that's not the case, if they're uniform, then you can't say for sure whether Alice has 0 or Bob has 0, okay? And a particularly interesting example is what happens when beta is 0 and gamma is 0, but alpha and delta are non-zero, okay? Then the state is really intertwined, like you have to describe the state jointly, and then that is an entangled state of 2 qubits. Okay? So this is a notation that you can use. What happens a lot when you're working with pages and pages of equations. You write them down. You wonder, gee, how can I reduce space or write things more compactly? That's how these shorthands come about, right? So a shorthand that is widely adopted is to just say, oh, this means this, right? So if you write 0, 0, that really means there's an implicit tensor product. Okay, so that's something you just have to get used to.
I'm sorry, I mean a stupid question. You said that a very interesting state is when alpha and delta are 0.
When
or maybe I misunderstood.
that would also be very interesting.
Oh, sorry, misunderstood. Okay, so what did you?
But what I said was the opposite of that. But
So
you identified another very interesting
exactly,
entangled state.
for me, alpha and delta equals 0. It's not very different than beta and gamma equals 0. They are both
That's right.
quite.
Exactly.
Yeah,
Okay.
and you can get from one to the other using what's called local operation.
Right.
And then you would discover the superdense coding effect. So we'll get to that later.
Okay, I can wait.
Okay. Tensor product for matrices. Sorry, this is a bit more math, but it's necessary because we're going to be taking, this is how we took the tensor product of vectors, and then we're dealing with density matrices. That's what we're describing as the states. We need to figure out how do you tensor matrices together, right? So it's the same rule, right on the left, right? So you take whatever's on the right and put it on top of each element of what's on the left, and then you multiply it out. So that's all this is saying. Okay? And then as an example, we were talking about density operators, density matrices. Let's generalize this example to matrices. I'll just write out what you get as the answer. Okay. So that's the first line. And then when you put the right on top of the left, you just get a 1 in the top left and zeros elsewhere. You get that. Okay? All right. And then it's useful to know what are the properties of the tensor product. These are kind of the rules that you need to know to play the game, right? So what are the rules? It's similar to the rules that you have for multiplication, right? So if you multiply tensor product by a scalar, you can take that scalar and multiply this vector by that scalar, or this other vector by the same scalar, and that's an identity. Okay. There's a distributive property, right? So if I have a superposition of 2 vectors, and I take the tensor with some other vector, I can tensor first and then take the superposition. Okay. Similar for the other side, you can do the same thing. So those are the rules of the game. Similar rules for matrices acting on vectors. This is where these properties are very helpful to just sort of internalize them, because you can imagine if you first say, okay, I'll take K tensor with L, write out the whole matrix, right? Take phi with psi, write out the whole vector, do the matrix vector multiplication. That's going to take a long time, right? But if you know this property, you can say, oh, okay, I can just take K and act on phi and L and act on psi, and then that's how I can think about it. So in the language of quantum information, and we're talking about Alice and Bob, these characters come up a lot. So suppose Alice has the first qubit, Bob has the second, and then suppose that Alice does something locally on her qubit and Bob does something locally on his. That can be described by the tensor product of these 2 matrices. And then we see it's kind of natural, right? Like it's natural that if Alice is doing something alone, this K, it would affect only her vector, her system, right? And if Bob is doing something alone, it would only affect his system. But if they do something jointly, then it affects the joint system. Okay. And then you have these kind of linearity properties, which are very nice.
That assumes that phi and psi are distinguishable to start with, right?
They don't have to be. These can be whatever. These, yeah. I mean, you could imagine that we're describing this physically, right? So Alice's qubit could be plus, right? 0 plus 1. And then Bob's qubit could be 0. Those aren't distinguishable. And then if they're doing these local actions, it's kind of natural that this local action of Alice would only affect her system, and local action of Bob would only affect this. So it's just a general rule.
But implicit in some way in that first line of K cross L is that the K acts only on the Alice
That's right.
and L acts only on the Bob.
That's right. Yeah.
It's not distributive in the way, I would have otherwise thought from the first lines.
Yeah. I mean, here we see something like the first line, right? This superposition of these vectors, and then this is like a linearity property. We can exchange the sum and the scaling with the K and the L. Right, so you see that happen. This matrix right here, this now corresponds to, if we were to try to interpret this physically, it's something more than just individual actions, right? So if this mu were a probability distribution, it could be like, oh, I'm choosing an action according to a coin flip. So I'm choosing this kx according to a coin flip, the lx according to a coin flip, and then you have this kind of convexity property, right? Where like the mixture of these operations is the mixture of the states that would result from doing these things individually, right? But mu, this is just general math, right? So this mu need not be a probability distribution. It could be any complex coefficient. Okay. There were tacos promised. I am not in charge of the tacos.
No, I think Sush actually was on his way to go pick them up. It's
Great.
probably traffic. Yeah.
Okay. Traffic, football game.
Cause he left, he actually left around, I think, like maybe 10 or 5. Yeah, around 5, yeah.
Okay.
So it might just be traffic.
All right.
Yeah.
Well,
Not to
He's a
say he
good
went
guy.
directly there, he may have made a stop.
Yeah.
He's on the way.
he's on the way.
Yeah.
All right, very good. Okay, the other important thing is how does the notion of the inner product of two vectors generalize to the tensor product, right? So if I have some tensor product of two vectors and the dual of the tensor product of those two vectors, it's the same kind of thing where you just take Alice's components and combine them together, and you take what Bob has and combine them together, right? So if I want to take the inner product of these two vectors, it's just the product of the inner product of the individual vectors, right? So that's a pretty important rule. Okay, those are rules. So let's talk more about how do we interpret this physically. So suppose that Alice has a qubit prepared in the state rho A, right? Bob has a qubit prepared in the state sigma B. Then if their systems do not interact, but they sort of put them together such that they can eventually interact, the state of the joint system is the tensor product of the individual states. Okay? That can be considered one of the postulates of quantum mechanics for describing the state of multiple quantum systems. And then the important question is who has what? We answer that by putting the system labels. It's a very useful bookkeeping device. Okay, this is a state we wrote previously. If both of their systems are in the classical state 0, we describe the quantum state like this. If they're both in the classical state 1, we write them like this. And then probabilistic mixtures, right? So this could correspond to correlated coin flips, right? So if you and I were to, you had a coin, I had a coin, it could be the case that every time we flip this coin, if I observe a 0, you observe a 0, right? That would be kind of interesting. And then similarly, if every time, you observed heads, I observed heads, you observed tails, I observed tails. That would be this classical state right here. So that's a classical state. That's it's a correlated classical state. Okay, but we can have a notion that generalizes this, and that's quantum entanglement. So I think this is not an actual experiment or anything. This is just art. Okay. Yeah, there's a whole story of Bertelsmann's socks, but I don't know if I'll tell that. Okay, so let's get to this phenomenon of quantum entanglement. So previously we talked about the state of Alice and Bob systems if they don't interact previously and then they're brought together. Okay, that's called a product state. The reason it's called product state is because the state can be written as this tensor product of the two individual states. There's something that generalizes that called a separable state. Okay, so what does this mean? We would flip the coin. If we would have access to, we would both have access to the outcome of the coin flip. If it's heads, I would prepare row 0. You would prepare sigma 0. If it's tails, I would prepare like row 1, you would prepare sigma 1. Okay, and then the state is the probabilistic mixture of the two quantum states. So the point is that this state can be prepared by what's called local operations and classical communication. The classical communication being this X, this letter X that's the outcome of the coin flip. So we would both have access to that and then prepare the state.
Okay, this notion of having to have the notion of both of us having to have access to the information.
To the classical information.
Right, to the classical. Like I hear that a lot. Is that why we don't have all optical quantum whatever or all quantum systems? Is it because of the fact that we have to have this classical interaction for us to be able to communicate what we have? So that we know the other.
We can have states that generalize this.
Yeah, what is the? I guess my question is, what is the? Only because I'm learning about this.
You could have a quantum interaction.
What is the importance of both of us having access simultaneously to this information? Say I get it later, you get it first. I mean, eventually we'll have to kind of come together and compare notes, so to speak. But you know,
this is meant to. This is a way of defining entanglement. So we're actually showing what is not entanglement, and then entanglement is the opposite of this.
okay.
So any state that cannot be written in this way is an entangled state, and is somehow quantum. Okay, because you need a quantum interaction to prepare an entangled state. To prepare this, you don't need any quantum communication. It suffices to have classical communication. Like I could flip the coin, send you the outcome, which over a classical phone line, and then we could prepare this the state's condition of the outcome of the coin flip.
Okay. So I may be asking something going forward once you start speaking about the quantum entanglement. Is that there's still some level of we both have to have access to the information at the same time in order to communicate that we.
It's that at some point,
right?
there has to be some kind of quantum interaction that takes place. It could be the qubits are in the same lab, and you do some quantum logic gate on them. For example, this C0 gate that comes up a lot.
Okay.
Another way is there could be a perfect quantum channel that connects us, right? Those are hard to make. that's what we're trying to make. But in principle, you might have a perfect quantum channel, and then what I could do is I could prepare some entangled state locally, send you one of the qubits over the quantum channel, and then we would share this quantum state. So that's something called entanglement distribution, and in fact, we'll talk about that later.
Okay.
I was just thinking, she might be thinking about, you know, whenever we go to use these states as a resource, there has to be some classical
Yeah,
communication.
we have to communicate. so
Like
we
for
actually have
teleportation.
to-
Oh,
Yeah.
yeah. Sorry, maybe I didn't answer your
Even
question.
with your latter example, even if we have a quantum channel that we send something over, eventually there has to be some classical interpretation of what we have.
That's right,
And
yeah.
but does that have to be simultaneous? Like, I'm assuming
No.
that happens, okay. So
No.
you can check that at any time.
So I mean, that's a very good question. We might want to check what state we have, right? So you could do this if you have many independent shares of this state. Like we could do this procedure many times by which we make this state. And then I could do local measurements, you could do local measurements, and then we would get some classical data, right? And then, as you're saying, to interpret that data and to sort of verify whether we have entanglement, we have to share that data. And this is something called tomography, and it's how you learn the state of a quantum system.
Okay, and that data has to be over the classical.
That data has to be shared.
Okay.
And we're actually going to get to that point later. If that doesn't happen, then there's no way to verify the global state. You can only verify what's called the local state. There's something called the local density operator. And that's what you could verify. That, for example, I could verify if I'm doing local measurements and I don't hear from you about what you did. Okay. Yeah. Okay. These states are called separable states. That's the name that was given by Reinhard Werner in 1989, and it's stuck.
Well, just mathematically, it's a separable equation.
Yeah, right. I mean, it's just this mixture of separable things. So then you say, okay, it's separable. Yeah, so it's fine.
I think a key is that you're using the p's and 1 minus p's, which are all real.
They're all real numbers. Yeah, that's a very important point. This is a probability distribution, right? I intended that to be the case. If you put complex numbers here, it doesn't have to be a classical state. Okay, you can realize other things.
But then it's not separable necessarily.
Then it's not separable, exactly. So, yeah.
From the basic, easiest way to understand it is if it's a mathematically separable equation, then it's not entangled.
Yeah, well, there's this very important point that these need to be probabilities to be a separable
They
state.
have to be non-negative.
They have to be non-negative. Yeah. Technically, if you want to extend this definition to positive semi-definite operators, not just density operators, then you could say the operator is separable if you have non-negative numbers here. Okay. But once you put complex numbers, then it need not be separable. So that's a very important point, this probability thing. But that corresponds to flipping the coin and then preparing states conditional on the outcome of the coin flip.
Which is non-causal in that scenario.
That's causal. Right. I mean, like, I did it first, and it could be that some other person flips the coin and sends the outcomes to us. That would be a causal structure. But I mean, you're right. I mean, if we just write this, it doesn't really tell you the causal relationship of how the state was created. Right? Okay. One thing we can do is we can use the spectral decomposition on each of these rho x's and each of the sigma x's, and then, if we spectrally decompose rho x, we would get some pure states. You could label them by x and y. And if we decompose this, sigma x, we would get pure states labeled by x and maybe some letter w. And then we can sort of just have a super label Z that means X, Y, and W. And then that's just a way of rewriting this separable state as a convex combination of pure states. So the point is that this can always be made equal to this for some other distribution. You can always find that. Okay? And then physically, you wouldn't be able to distinguish this from that, right? Because it would be the same density operator, and if the state of quantum systems, of two quantum systems, are in the same, described by the same density operator, then they are physically indistinguishable. There's no experiment you could ever perform to distinguish them. Okay. This is just somehow a useful thing that you can always write them as convex combinations of pure states. Okay, so then the big definition is entangled states are not that. Okay, so it's defined in this maybe negative way. And a very important question you might have is, suppose I'm given the mathematical description of a density matrix like rho AB. So if I hand you a list of numbers arranged in a matrix, if it's a 4 by 4, it could be interpreted as the state of two qubits. Very important question is, you might want to decide, is this state entangled or not? Okay. That's called the quantum separability problem. You can decide it for small matrices, but as the matrices get larger and larger, it's harder and harder to decide it. Okay? In a computer science sense, the problem is what's called NP hard, which when you hear that, that just means really hard. Okay, and there's a technical definition for that, but we won't talk about that. What's an example of an entangled state? That's what we talked about earlier, right? I said, pick the beta, the gamma to be 0, the alpha and delta to be 1, right? We had this alpha 0, 0, plus beta 0, 1, plus gamma 1, 0, plus delta 1, 1. If we set beta and gamma to 0, alpha and delta to 1 over root 2, we get this. And then we use the shorthand that I talked about earlier. Okay? We get this, and then the density operator is this phi with phi. Okay? This is a very important state of two qubits. It's called maximally entangled state. There's ways to measure entanglement, and according to most reasonable measures, this will have the state of it's the state of the largest amount of entanglement of two qubits. Okay? And it's like a unit. When we think of quantum information, we can think of this as a unit resource, like a fungible resource that you can use for tasks such as superdense coding, teleportation, quantum key distribution. Those are the big ones. Right? It can be used in quantum computation. Teleportation is a very important primitive for quantum computation. And when you start quantifying entanglement, we talked about qubits, you can also have e-bits, okay? And so that just means entangled bit. So this is, in a communication resource theoretic sense, an e-bit.
Does that mean an entangled qubit?
An entangled state of two qubits.
Of two,
So then it is somehow abbreviated to e-bit.
So that's the e-qubit.
E-qubit is too much.
Right?
So this will not be something you can write as that sigma p that you had on the previous slide.
That's exactly right.
You
Yeah.
never get any decomposition of it.
Right, so the thing that's hard about this is you have to look over all possible decompositions that you could consider, right? And that's with respect to all possible bases. And you can prove mathematically that it's impossible to write it in that way. And I think I might have written a short justification for why that's true. Okay.
At the University of Alabama Huntsville,
Yeah.
to show to prove that with the non-equal sign in the equation on the previous slide was one of the qualifier exam questions.
What was the question? Sorry.
So what I was saying is that one of the PhD qualifier exam questions at UAH was to show the proof that the entangled state equation is not equal to that.
Oh, really? Okay, interesting. Well, the answer is on the slides.
Yeah, right.
So
But
there you go.
between the two is a lot of work.
Yeah, no, it is a lot of work. Yeah, it's not simple. That's why it's underqualified. Okay. So if you wrote this out in matrix form, it would look like this: the ones in all of the corners, okay, and the 1/2 normalization, such that the trace, the sum of the diagonal elements, is 1. So this is the proof. I said consider that, right? So it's not the full story, right? But it's sort of like it is possible to prove. You take any psi of a qubit, so any possible unit vector for a two-dimensional system, any possible phi, and you can prove, I think it just amounts to Cauchy-Schwarz inequality, right? So if there's one thing to know from mathematics, it's the Cauchy-Schwarz inequality, right? like that's the first thing you do when you try any proof, and then if it fails, you get in touch with a mathematician. Okay, so you can prove using Cauchy-Schwarz there's this upper bound of 1/2 on the inner product between the entangled state and any possible product state. Okay, and then that tells you that it simply cannot be written as a product state. For if it were possible, you could have the inner product equal to 1. Right? A unit vector overlap with itself, the overlap is 1. Okay? So you just do something with Cauchy-Schwarz, and then you see this, as far as I remember. Right, so to pass the qualifying exam, you should remember Cauchy-Schwarz. Okay, so